Hello, my name is Frank McKenna, and in this short presentation I will attempt to answer the question, what is OpenSeas? To answer the question of what it is, I must talk a little bit about where it came from. While the genesis of OpenSeas was my dissertation, OpenSeas would not have existed if it was not for the creation in 1998 of PEER, the Pacific Earthquake Engineering Research Center. The person responsible for the simulation area within PEER, my former advisor at Berkeley and the current president of UT Austin, Greg Fenves, he had a vision for simulation. He wanted to use modern software techniques to create a new, extensible, and open-source finite element software platform for earthquake engineering. This software would encompass both structural and geotechnical engineering. For PEER researchers, this software would provide a common research platform within PEER to both educate students and share their work amongst themselves. The software would also foster a mechanism whereby new research developments made within PEER could be disseminated to industry faster than was previously the case. The software that President Fenves proposed came to be known as OpenSeas. OpenSeas stands for the Open System for Earthquake Engineering Simulation. What OpenSeas is an open-source framework for creating finite element applications in both structural and geotechnical engineering. While it is primarily used in earthquake engineering, it has also been used by researchers studying the effects of wind, fire, and wave on structures. OpenSeas is free for anybody to use, with the exception that you cannot sell software that includes OpenSeas source code without paying a license to do so from the University of California. Some stats on OpenSeas. OpenSeas has been under development by PEER since 1998. NEAS, or the Georgie Brown Network for Earthquake Engineering, supported its maintenance from 2005 through 2014. OpenSeas is primarily written in C++, C, and Fortran. The glue language that binds the code together is C++. There have been many developers from around the world who have contributed source code to the framework. There is an awful lot of elements, materials, integrators, algorithms, and solvers that these developers have provided for you to use. Now, as we don't expect users to actually build C++ applications, we have provided a number of pre-built applications for users to download and Amazon machine images for running the applications in the cloud using Amazon EC2. These freely available applications have led to widespread usage. The OpenSeas application is widely used around the world. As you see, in 2014, there are only a handful of countries in the world in which OpenSeas was not used. There are over 10,000 downloads of the sequential application each year. Now, while we do not know how often these applications are used, we do know that the parallel applications available on NSF Exceed resources utilize over 1 million CPU hours yearly. So what are these applications used for? OpenSeas applications are used for structural analysis of buildings and bridges, the geotechnical analysis of soils, and the combined models consisting of both structures and soil models. So how does OpenSeas compare with commercial software costing many thousands of dollars? This slide from Professor Jinxing Liu at Tsinghua University in the People's Republic of China shows how OpenSeas compares with the commercial application MARC for the prediction and the response for two large structures. As Professor Liu and many other researchers who have performed similar studies have found out, OpenSeas will give similar results to other applications for similar models. The results will be the same if and only if the models and the analysis are the same. So if OpenSeas is so capable, why is everyone not using OpenSeas? Most finite element applications have a graphical interface. With a graphical user interface, you build the model visually in front of your eyes with mouse clicks, pull-down menus, buttons, and text boxes. OpenSeas does not have a graphical interface. Instead, OpenSeas is what is known as an interpreter. The input is your keyboard. Let me demonstrate. Here I am in a Linux shell, though this could also be a DOS prompt in a Windows terminal application. With the correct installation of OpenSeas, I start OpenSeas by simply typing OpenSeas at the prompt. This starts the application. As you see, OpenSeas is just sitting there waiting for me to do something. Let me now ask it to spit out the string hello world. I do this by typing at the terminal. I type the command, put s, followed by the string, hello world. That was trivial. Let me ask it now to spit out that string 10 times. So I'm going to set I equal to 1, while I is less than or equal to 10. There we have it. Now OpenSees is still waiting for me to enter more commands. To exit the program, I simply type exit. The typical way people use an interpreter is not by typing the individual commands at the keyboard like I just demonstrated. Instead, the user will type the commands into a file and then run the file through the interpreter. Let me demonstrate again. Here I am back again in my shell window. Instead of typing the commands at the keyboard, I'm now going to enter them into a file. We're going to create a file, hello.tickle. And now in this file, I'm going to enter the commands I put in the previous example. For I equal to 1, I less than increment I by 1, put s hello world. I'm now going to save that application and exit. To run the application, I simply start my program, OpenSees, with the script name as the input argument. There we have it. Now, to quickly change what is being output or change the working of the script, all I do is simply go back into my input file and change it. And then once I've made the change, I just run it again. And there we have it. Because OpenSees is an interpreter, the input files that are run are actually programs. These programs are written in a programming language called Tickle. Tickle is a scripting language that we have extended for finite element analysis. The extension is done at a very low level, meaning we give you access to the OpenSees classes and class methods directly. While this means that to learn the program will typically take you longer, it is a more powerful approach that in the long run will allow you to do more things more quickly. If you exploit the fact that OpenSees input files are programs, you will be able to do many great things. You'll be able to create your own model building templates. One person in an office, for example, can create something akin to a spreadsheet that everybody else can use and by simply modifying the needed fields. With this, you will be able to perform parameter studies and perform the analysis in parallel on your model. Let me demonstrate with an example using the standard 2D steel moment frame. So, what would the Tickle code look like to generate the model? In 15 lines of code, we can define our model properties and build our finite element model. This can be done because we can use abstractions such as material properties, matprop, building properties, building prop, to create an outline of our model properties. And then, with our model properties defined, we can invoke a predefined CAN procedure that will go off and generate our model, given the input. The advantages of using abstraction and procedures are many. The complicated part of the code is the procedure. We only need to build this procedure once. We let the expert in the office do it. Everybody else gets to use this procedure. This approach is less error-prone. For example, instead of having to click to see if you got the right section for every element or location of all the nodes, you can just look at the list. In fact, it is so trivial, even your boss could check it for errors. And because it is so quick to build the model, this will allow you to do other stuff. For example, let's do some simulations to understand the response of our model to various inputs. We have our original 15 lines of code. Now, with 5 additional lines, we can quickly run a number of ground motions with different scale factors through our model. And as this is so trivial, in another few lines of code, we might modify the material parameters or even modeling options to look at the sensitivity of our results. And before you think this is going to take too long, we add 6 more lines of code to have the whole thing run in parallel on the multi-cores of our desktop. It's simple and easy to do, but only because the flexibility that the interpreted application OpenSees provides. GUIs simply cannot do this. OpenSees is a powerful tool, but only if used to its full potential. Like any software, a little bit of thought before you use it will save you an awful lot of time. In short, what OpenSees is a powerful tool for performing finite element analysis. It's free, its inputs are scripts, and the scripting aspect of it is something you will truly learn to love. However, like any software, it takes time to learn, but ultimately, it will save you time when generating your models. Time that can now be devoted to looking at your modeling assumptions and obtaining information on the sensitivity of the model response to various input parameters using the parallel computing resources available on any computing device, with the possible exception of our phones. Of course, a disclaimer is in order. OpenSees, like any tool, requires that the user understand the theory and limitations before use. Its output is only as good as the input. We do not protect you from yourselves. The user needs to study the results to ensure that both the user and the program are providing results that represent how the actual system will behave. You are the engineers, and you need to ask yourselves, do these results make sense for your particular structure? I thank you for your time.